plane mirror. I'll keep here a source, a luminous point object or luminous point source, let it be. So it's going to emit a ray of light in all directions. And now there are two set of rays. One, a rays emitted directly by it will reach the screen. So these are the two direct rays. So this particular thing, vertical line is what? It will be like a screen. So the luminous point object, it will emit light in all direction. Let's assume that it will emit light in all direction. So a rays which will directly move from the source to the screen, I'll call that as a direct rays. That is what I'm showing here. Like these are the direct rays. Already once again, I'm showing it. Fine. These are direct rays. Then, okay, let's go back to the plane mirror concept. If you keep an object here, and if there's a mirror, where its image will be? Its image will be here. Because what is the basic idea? Object distance must be equal to image distance. Now, what is the object distance? D naught. What is the image distance? Should be D naught. So, and how do we measure that object distance? Normal to the mirror. So therefore, what is S? S is the source which we have kept it. S dash is what? Its corresponding image. Okay, now after this. So this particular source will emit a monochromatic light of wavelength lambda. So then its corresponding image also will emit the same light of wavelength lambda. So here let's get into the mirror concept first. The rays emitted by the source, so they will strike at M1, and after reflection they will reach the screen at point P1. And from the plane mirror concept, if I extend this reflected ray, if I produce it back, so where do it will meet? It will meet at S dash. So as if what will happen? This reflected ray is being emitted by its image S dash. Similarly, a ray emitted by source S after striking M2 will reach point P2 on a screen. Will reach point P2 on a screen. Now, if I produce it back, it will emerge as if from S dash here, this reflected ray. So in this way, so what do we get here? Like a on screen, we'll get a direct rays and also the reflected rays. Is there any path difference between direct ray and the reflected ray? Look at these two. Is there any path difference? Yes, there is a path difference. If this path difference equal to n lambda, we'll get here maxima. If the path difference equal to 2n minus 1 lambda by 2, then we'll get a destructive interference or a minima will be obtained. So like this, what we can see is like a on the screen. So we are going to notice a alternate bright and dark bands. Why do this interference bands are noticed? Due to superposition of direct waves and the reflected waves. So in this region only, we'll see the superposition of the direct rays and the reflected rays. Therefore, the interference pattern will be noticed only in this region P1, P2. What about P2O? Why there won't be any interference pattern? Because only the direct rays can reach from a screen. You can see this. Only direct rays can reach. What about the reflected rays? Reflected rays cannot reach here because what is OP2? OP2 will be out of field of view. So we don't get any reflected rays in this region. Similarly, there won't be any reflected rays in this region. Any reason for that? Because the reflected rays, this is the field of view. So where do we can see the interference pattern? Only in the field of view of the mirror. Simplest way. So interference pattern, where do we notice? So we'll notice that noticed in the field of view. Okay, this is something very important, I feel. There's one simplest way I can roll. Okay, how to get the field of view? I think you know the reflected rays. Means the reflected rays where they touch the screen, where they go and strike the screen, and this particular part, what happen will be a like a the part of screen which will lie in the field of view. There, what we notice is like a there what we notice. So we notice here in this region, the reflected rays what happen will go and strike the screen in this region. So there's nothing but this everything will become a field of view. Means a part of a screen which will be lying in the field of view of the mirror. What happen there only the interference will be obtained. Okay, able to I think interference pattern notice in the field of view. There's a one condition. Okay, got it now. Why OP2 and P1 P or above P1 P? Why there's no interference pattern? Because only the direct rays reach that part of the screen and the reflected rays will not reach the screen. And where do we see interference pattern? Only in the region, a part of screen which lies in the field of view of the mirror. There, what the interference pattern will be noticed here. Okay, there's a one core idea. Okay, now we will summarize it. So what do you mean by this one? A, a part of screen that lies in the field of view that lies in the field of view. I think sentence like the interference pattern is formed in a part of screen that lies in the field of view. Interference pattern is formed on a screen that lies in the field of view. Okay, this is the one very important statement which will help you a lot when you're going to take any numericals. Let me put that order on a screen that lies in field of view of mirror. Okay, got this. So there's a one very fundamental one, very important. Okay, now let's get into the. I want to know the fringe width, where the positions of maxima, other things. So prior to that, we'll go for one more. If a ray reflected by a denser medium, it will undergo phase change of pi radian. So what is the basic idea? Now let's look at this particular thing. There are two rays are there. Or I'll draw a better diagram. Okay, let this be a mirror. Then let this be a source. So I'm going to consider two set of rays. This will have the phase angle of pi. Okay, this is having a zero phase, zero phase. By the time it arrives here, this will have a phase phi. This will have a phase phi, whereas this will have a phase angle of phi plus pi. Okay, let me bring the pointer. Let me bring the bigger dot pointer. Okay, no. You look at this particular ray. There's a ray 1. It goes and will strike the point M2 of the mirror. And we know when a ray reflected by a denser medium, it will undergo phase change of pi radian. So it was both, the source will emit the rays with a zero phase. Then as the wave propagates, it will acquire a phase. By the time it reaches one end of the mirror, it will acquire a phase angle of phi. Then here what happened due to reflection, because it's reflected by a denser medium. Mirror is a denser. The above the mirror, let there be air. This medium is air. So what is the refractive index of air will be less compared to mirror. So after reflection, the wave will undergo a phase change of pi radian. What about the ray which is just above point M2 will have a phase angle of phi. So is there any phase difference between these two waves? Yes, there's a pi radian. Then if they undergo superposition, we know that if the phase difference between two waves is pi radian, then they'll undergo destructive interference. So therefore, what do we notice just above point M2? A dark spot. So just above M2, so what we notice is like it will be a dark spot. So here what will be noticed? A dark spot. Just above M2, a dark spot is noticed just above M2. Why that dark spot will be noticed here? Just at this particular point, a dark spot will be noticed. Why that dark spot? Because the ray 2 and ray 1 will undergo destructive interference. The ray 2 and 1 will undergo destructive interference. Because of that, what happened? We notice a dark spot here. This is the ray 1, this is the ray 2. This is very important. Means whenever a wave reflected by denser medium, it will undergo phase change. Due to that phase change of pi radian, it will acquire additional path of lambda by 2. And if the path difference is lambda by 2, then the rays must undergo destructive interference. Okay, got it now? So now what I do is like, if I move this mirror, if I move this screen, if I move this screen and such that the point O touches the M2 of the mirror. So where do I'm showing? I'm showing it in this diagram. I'll move the screen such a way that the screen will come in contact with the one edge of the mirror M2. Then what do we notice? I'm going to notice a central minima, or what you can call that as like a minima will be noticed, not maxima. Any reason for that? Because the phase difference between the ray 2 and ray 1 just at M2, just above M2 will be 0. So therefore a minima will be noticed here. Now, as I move the screen away, so as I move the screen away from the one edge of the mirror M2, then open that particular dark spot will not be noticed. The dark spot or the minima will not be noticed here. So here central minima, okay, here because no superposition, so central minima pattern is not visible. Only a part of a interference pattern is visible. Total interference pattern is not visible. It's correct. This part is missing. Only a part of interference pattern what happened will be visible for us. Now what I'm interested, the position of maximas and minimas and also the expression for the fringe width. Okay, let's get into the mathematics here. Now let me consider the path difference of the rays SM2 and M2P. So let me consider the path difference between the rays. Between what? Like between SP2 and S dash P2. I'll consider these two rays, a ray 1 and another ray like this. So is there any path difference between these two rays? Once again, I'll put it. This ray will cover a path SM2 plus M2 P2 to reach screen at point P2. And a direct ray will cover a path of how much? SP2. So what is the path difference? Okay, now I'm going to write path difference. So this is how much of path it will cover? SM2 plus M2P2 plus lambda by 2. Why plus lambda by 2? Because it has undergone a, because it is reflected at M2, the ray what happens will get reflected by a mirror. It will undergo a phase change of pi radian. Due to pi radian, how much of additional phase it will gain? Lambda by 2. This lambda by 2 is due to what? Due to reflection. Due to reflection by a mirror. Okay, we'll indicate that due to reflection of a ray by a mirror at M2. At point M2. So due to that, what happened? It is there, that one. Okay, now what about the other path? Okay, what about the other ray? The other ray will cover a direct ray. What happened? How much of path it will cover? It will cover a path of SP2. Write it here now. This is the path difference of the rays are having at P2. Okay, now let's come for this one. Is it from the mirror object distance should be coordinate distance? So from the triangle S, M2 or say like A and S dash, M2 and A, these two will become similar triangles. So from similar triangles, what we can write here like a SM2 is equal to S dash M2. SM2 is equal to S dash M2. So SM2, I'll write it as S dash M2 plus M2P2 plus lambda by 2 minus SP2. Then further, S dash M2P can I, and M2P2. This everything what I can write it as S dash P2. Sum of this distance plus this distance. How much it should be equal to? S dash P2. So the sum of these two are depend together, write it as S dash P2. No, SP2 is a direct wave and S dash P2 is like a reflected wave. Then from the YDAC setup, that one. So compared to S dash P, how much of, so compared to SP2, how much of additional path the SP2, F dash P2 will cover. So there's additional path. Looking at the diagram, compared to SP2, how much of additional path F dash P2 will cover. This is the additional path. So what is the delta X? So I'll take help of this triangle. You can see clearly the triangle. So what is the triangle? S dash. So shall we write it because sine theta equal to delta X by 2D naught, or time being you write it D. This one. So therefore, what we can write it as the delta X is equal to, so this S dash P minus S2 SP2, we'll write it as D dash here. I think some symbol change, some correction is there. Delta X dash alert. So what is the delta X, sir? How you brought all that delta X dash? So let me write that sine theta is equal to delta X dash by D. What is delta X dash is equal to S dash P2 minus SP2. Okay, justified. Writing D sine theta. Delta X is the net path difference. Okay, now after simplification of this, okay, now D sine theta. Further, theta very small, sine theta will become tan theta, and the tan theta from the triangle will become equal to y by capital D. So from where you are writing tan theta equal to y by D, I think I should generate one more triangle for this. you are able to see. So now let me. Look at now. So this will be the f dash. We'll write it. Same already in YDSC or come across. That's a similar idea here. Nothing is there. So this will is what I'll call that as theta. D sine theta. And this is what theta. This is theta. This is Y. This is capital D. And this is what delta X dash. Okay, now what is tan theta? You can write it as Y by capital D. So here Y max you write. There's a reason why it has become like this. So look at this equation. In place of d sine theta, what we can write it as tan theta, where that further tan theta, theta very small, sine theta will become tan theta. Further tan theta from this diagram, I can write it as y max by capital D. Writing that y max by capital D, I'll get expression for y max is equal to, look at this equation. Y max is equal to, let me bring the y max is equal to n minus 1 by 2 lambda capital D by small d, that one. So this will give the position of nth order maxima. Similarly, I want the position of nth order minima. In that case, what we should do, the path difference delta x should be equal to 2n plus 1 lambda by 2. Lambda by 2 get cancelled. So the position of minimas are given by this equation. Y minimum equal to n lambda capital D by small d. Okay, fine. So this is about the interference, the position of maximas, minimas, how to calculate. Next question comes like how to get the fringe width. How to calculate the fringe width. Okay, that will do one thing. How to calculate the fringe width? Fringe width should be equal to, put n equal to 2 and put n equal to 3, or n equal to 1, you write n equal to 2. So this will be fringe width should be equal to y2 minus y2 minus y1. So what is y2? Y2 should be equal to 2 minus 1 by 2 lambda capital D by D minus 1 minus this will be 3 lambda capital D by 2D. This will be lambda capital D by 2D. So lambda capital D by small d. So this is the expression for the fringe width. Okay, how many fringes will be noticed on the screen? So number of fringes on the screen. Number of fringes on screen. That should be equal to how much? P1, P2, I'll call n dash, P1, P2 by W. What is P1, P2? This particular distance. So that has to be determined from the geometry. So how many fringes that are noticed on the screen? Number of fringes on screen that are visible. Not all the fringes will not be visible. Only part of a pattern will be visible. So therefore, I'm asking how many fringes are visible. So from geometry, we'll calculate P1, P2 by fringe width. Will give number of fringes that are visible on the screen. Okay, there's one overall basics idea of the Lloyd's mirror. Okay, once again, I'll show everything content. You can in fact see it. So basically, so there's a one setup. So in the Lloyd's mirror, what do we get? We get central minima or central maxima? central minima will be noticed here, not central maxima. And when do that central minima will be visible? Only when screen touches the only when the screen touches the one edge of the mirror M2, then the central minima will be visible. Otherwise, the central minima will not be visible and some fringes will be missing. There's an overall idea of the Lloyd's mirror. Okay, now you can ask questions, sir. What is the use of this? Okay, some interference pattern we are learning. Oh no, not like something to study interference pattern. This experiment is there. Basically, this I can use to determine the wavelength of light. Wavelength of light is a difficult quantity to measure. I can very easily measure the wavelength of light with the help of this one. So now we know the fringe width idea. Okay, we'll explore using this particular thing. No, if you see this, so if I have, so this is the two, like a source S is there. I'll keep a mirror. Let me keep at a distance like a. Then what I do is like, I'll keep a screen here. Then I'm going to measure the fringe width. So let lambda 1 be the wavelength of the source. So there's a source S1. So then corresponding S1 dash will be formed, and we know the interference pattern. Let me redraw this. Okay, there's a ray 2. There's a ray 1. There's a ray 1. Okay, now if you see this, I'm going to see the interference pattern. So let the fringe width of the pattern here, let it be. So here is what the interference pattern is, what we are going to notice. So let W1 be the fringe width of that one. So what is the formula for fringe width? How do we write it here? So in this case, this will be D1. So what is the W1 is equal to lambda 1 capital D by 2A, because what is the distance? I'm going to I'm going to increase the distance from A to A plus X or A plus Y, I'll make it. Or A plus B, I'll make it. So I'm just going to shift this source above. Let me write it here. The fringe width W1 equal to lambda 1 capital D by 2A it is. Okay, let it be lambda, wavelength of light. Then what I do is like the same mirror, everything, all the setup is same. There's a screen. The source, I'm going to shift it above. So what is the distance of now will be A plus B, where the corresponding image will be formed at A plus B. Then again the light coming from here get reflected and reach the screen. The lights incident at other end after reflection will reach here. So here. So what is this quantity? A plus B. So this is the same source. Now this source, I'll call it as S2. So this will become S2 dash. The same source. The wavelength is also, I'm not going to change it. So there's a ray 1, there's a ray 2. Here again, I'll see the interference pattern. I'll measure the fringe width now. Will be W2. Why? Because the distance between has changed, Earlier, what was D1? lambda. Okay, so some symbols is there. Just do make notice. Lambda d by 2a. So what is d1 is equal to? D1 is equal to 2a. In this case, what is d2? D2 should be equal to 2 times of a plus b. So what is the fringe width I'm going to measure? Lambda capital D by d2. So what is d2 equal to? 2 times of a plus b. So w2 equal to lambda by 2 times of a plus b. Can I measure w1? As I can measure this. I can measure w2. I know a and b. With that, what will happen? I can calculate the lambda. Or no, sir. Like I'll change wavelength also. Let me introduce here. Let me introduce in this way the condition. No, sir. Let wavelength be different. Okay, no problem. Put it here. Now, what is capital D? Capital D is what? This will be known. Okay, look at all the conditions. Sir, here also you should change as I change it. So this will become again. You can do experiment in your own way. There's nothing. Now you can see things clearly. I know lambda 1. I know lambda 1. This one. So I'll do the experiment and let the source be at a distance a from the mirror, this mirror. So then what is a W1 fringe width equal to lambda 1 capital D by D1. What is D1? D1 should be sum of these two. The distance is how much? Equal to 2a. Okay, fine. Next again. I'll take another source. Let it be at a distance a plus b. Then what is the D2 should be equal to? This length, object distance should be equal to image distance. So therefore it will become D2 equal to 2a plus b. Fine. Okay, now the same mirror is kept here. I'll measure the fringe width. I know W1, lambda 1. I don't know capital D. Okay, leave it. This one. So D1, you know it. No, you know W2. You can measure using traveling microscope. You can measure W1, W2. Then lambda 2 is unknown thing. So A and B are known. So you can calculate the lambda 2. So like that, the wavelength of the source of light can be determined using Lloyd's mirror. There's a major application of Lloyd's mirror. We can determine the wavelength of light of a given source. What is the wavelength of that light emitted by that given source can be determined using Lloyd's mirror. Just we need one plane mirror and we need a traveling microscope because here the bright and dark bands are noticed. No? So then with the help of traveling microscope, I'll determine the fringe width. Once I get the fringe width, I'll substitute here. I'll substitute a W1. Then I'll use this particular formula. I think this will be lambda 1. Okay, fine.